Hello, and welcome to this presentation, Getting Started with the ZNB3000 Distance Default Measurements. In this presentation, we'll show how to configure and make distance default measurements using a Rohde Schwarz ZNB3000 series vector network analyzer. This presentation assumes a basic familiarity with distance default measurements. If you're unfamiliar with distance default measurements, or if you'd like a brief review, you may want to watch the presentation Understanding VNA's Distance Default Measurements before beginning this presentation. Distance default measurements provide the location of possible faults in a transmission line or cable and are supported on all Rohde Schwarz ZNB3000 series vector network analyzers. Using this application requires the K3 license option. The ZNB uses frequency domain reflectometry to determine the location, as well as the severity, of reflection points or faults. Results are plotted in the form of return loss as a function of distance. Note that it's also possible to perform distance default measurements in the time domain, but we won't be covering time domain DTF measurements in this presentation. There are 6 basic steps in making distance default measurements: enabling the measurements, configuring start and stop distances, configuring the frequency sweep, selecting or defining the cable type, performing a one-port calibration, and viewing and/or analyzing the results. In the remainder of this presentation, we'll go through each of these step by step on the ZNB3000. DTF measurements are configured by pressing the Trace Config hard key or by selecting this option from the ZNB3000 menus. First select Distance Default, and then switch the distance default measurement to On. Next, the start and stop distances for the measurements must be entered. Note that results will only be displayed for events occurring within this distance range. In addition to a distance range, a frequency range must also be configured. This is done under the Stimulus group. Frequency range is important because the maximum distance default that can be measured is inversely proportional to the frequency span. In other words, the smaller the frequency span, the greater the maximum distance. However, decreasing the frequency span will also decrease the distance resolution, so frequency range should be chosen with this trade-off in mind. The output power of the tracking generator can also be configured, and it's important to remember that too low of an output power may lead to inaccurate measurement results, especially for very long cables and/or cables with high loss or attenuation. Next, let's discuss sweep points. The auto number of sweep points can be used to obtain the best distance resolution. This function automatically determines the proper number of sweep points to use for a given user-entered maximum distance default. It's possible to manually configure the number of sweep points using the sweep hard key, but if the manually configured number of points is too high or too low, the ZNB will display a warning message and will automatically reduce or increase the number of sweep points as needed. The next step is configuring the cable type. Cables are defined by 2 main parameters: their velocity factor or relative permittivity, and their attenuation, which will vary by frequency over a specified range. Available cable types can be used to view both predefined and user-defined cables. The ZNB3000 comes with over 50 predefined cable types, and cable types can be easily added, modified, or deleted. We'll provide an example of how to do this in just a few moments. As mentioned earlier, a cable type or model consists of a user-friendly name, the relative permittivity and/or velocity factor of the cable, and the attenuation of the cable at different frequencies in units of dB per meter. When defining a cable type, only permittivity or velocity factor needs to be entered. This is because velocity factor is simply the square root of permittivity, and the ZNB3000 can therefore easily calculate one value from the other. To add a new cable type, simply press Add and specify the values we just discussed. The cable attenuation can, however, be specified in two ways. The most common and the most accurate of these is using a table that contains attenuation values in dB per meter at different frequencies. The ZNB will interpolate values between these frequencies. The other method is entering a single frequency value and letting the ZNB3000 calculate frequency-dependent loss. Because loss is one of the factors used when determining distance to fault, it's important to specify the cable's attenuation values as accurately as possible. And finally, cable type parameters can also be imported from a user-created file. To run a DTF measurement, the far end of the cable under test must be terminated into a well-matched, or roughly 50 ohm load. This load may be a cal standard, a dummy load, or an antenna that's resonant at the measurement frequency. Erroneous distance to fault measurements are often caused by a failure to properly terminate the far end of the cable. The near end of the cable can be connected directly to the ZNB3000, or the cable can be connected using a short, high-quality DUT or device under test cable. A DUT cable may be helpful when the near end of the cable under test is difficult to access. Using a DUT cable also helps to avoid strain on, or damage to, the ZNB3000 connector. As we'll see in a few minutes, the effect of this DUT cable can be removed via calibration. The next step in DTF measurements is to perform a one-port calibration. Calibration defines the so-called reference plane and normalizes the trace. The calibration process involves sequentially attaching an open, a short, and a match or load to the location where the cable under test will be connected. These standards can be in the form of discrete standards, or they may be combined into a calibration T. In addition to these manually attached standards, electronic calibration units can also be used. These units switch their internal standards in and out automatically and are controlled by the ZNB3000. If the cable under test will be directly connected to the ZNB3000, then the calibration standards or calibration unit should also be connected directly to the ZNB3000 port. If, on the other hand, a DUT cable is used between the ZNB3000 and the cable under test, then the calibration standards are connected to the end of the DUT cable, since this is where the cable under test will be attached. Attaching cal standards to the end of the DUT cable allows this cable to be calibrated out of the measurement results. Let's now look at a DTF measurement result, which shows return loss as a function of distance. Values can be visually read off the graph, or markers can be used to obtain more precise values. Here we see a single large fault, which appears as a spike in the graph, and placing a marker on this fault shows that it appears at a distance of approximately 6.8 meters. Generally speaking, the larger the spike, the higher the level of reflection at that point, and the more serious the fault. But it's worth mentioning that smaller faults may be caused by reflections from connectors, splices, etc. The fault limit check function displays a list of faults above a user-defined limit, and this can be useful in differentiating between actual faults and other reflection points along the cable. This limit is defined relative to 0 dB. Here we've set a limit of minus 20 dB, so the larger fault at 6 meters appears in the table, but the smaller fault at approximately 10.5 meters does not. The list of detected faults can be exported as a file. And lastly, leaving tracking on causes the table to be cleared and refreshed after each sweep. Unchecking this box will freeze the table contents. Let's end with a brief summary. Rohde Schwarz ZNB3000 series vector network analyzers can be used to make distance to fault measurements, which provide information about faults or reflection points on an attached cable. In order to perform a distance to fault measurement, the user must specify a cable type as well as the start and stop distances. In addition, the frequency range for the measurement must be given. When making distance default measurements, it's important to remember that the far end of the cable must be terminated into a well-matched load. Accurate DTF measurements also require a valid one-port calibration. Measurement results are usually displayed in the form of a graph showing return loss as a function of distance, although faults can also be shown in table format. This concludes our presentation, getting started with the ZNB3000 distance default measurements. If you'd like more information about network measurements, distance default measurements, or network analyzers from Rohde & Schwarz, please see the links in the video description. Thanks for watching. Please subscribe to our YouTube channel and visit us at rohde-schwarz.com.